Okay, notes 3.6, calculating higher order derivatives. So higher order derivatives means we can take the derivative not only one time, but we could take it infinitely many times. So the second derivative, the third derivative, or all the way up to the nth derivative. So this first part is talking about notation. So if everything is in terms of y, then we have y prime as the first derivative, y double prime as the second derivative, and y triple prime as the third derivative. Or in other words, this is just y to the nth power, okay, indicating how many derivatives we're taking, okay? Same with if this was in terms of f of x, this would just be f to the nth of x. And then if we do it in terms of dy dx, notice that the second derivative is d2y dx squared, the third is d3y dx cubed, which means the nth would be dny over dx to the n power. Okay. So for this example, it wants us to continue and find all the derivatives given. So the first derivative, the second derivative, the third derivative, and then the fourth derivative. So taking the first derivative, this would be 6x to the fifth minus 8x cubed plus 10x minus 3. Okay, now I'm no longer looking at this one. I'm now looking at the first derivative to find the second derivative. So that would be 30x to the fourth minus 24x squared plus 10. And then again, I'm not looking at this one anymore. I'm going to look at the next one to find the third derivative. So this is 120x cubed minus 48x. And then to find the fourth derivative, I'm going to be looking at the third derivative. So this is 360x squared minus 48. Okay. We could keep doing this until we end at 0, which means I could take the fifth derivative, and then I could take the sixth derivative, and then I can probably take the seventh derivative until I got to 0. Okay, remember this is the slope of the previous derivative. So in this example, I know that I could rewrite this as x to the 1/2 power plus x to the negative 2. Well, dy dx is the first derivative, so this would be 1/2 x to the negative 1/2 minus 2x to the negative 3. d2y dx squared is the second derivative, so then I have negative 1/4 x minus 3/2 plus 6x minus 4. Okay, and this one only wanted to take two derivatives. Okay, now what if it wants us to find the second derivative with implicit differentiation, which means we are taking the derivative in respect to y. So we have sine y is equal to x plus y. Well, to take the derivative, this would be cosine y dy dx is equal to 1 plus dy dx. Okay. Then we would want dy dx on the same side, so cosine y dy dx minus dy dx is equal to 1. So this is dy dx times cosine y minus 1 equals 1, which means dy dx is equal to 1 over cosine y minus 1. Okay, that would be the first derivative. Now to find the second derivative, which means we are finding the derivative of the first derivative. Okay, so we could rewrite this 1 over cosine y minus 1. So dy dx can be rewritten as cosine y minus 1 to the negative 1 power. Make it easier for me to take the derivative. Okay, which means that d squared y over dx squared is equal to negative 1 times cosine y minus 1 to the negative second power. That's the outside. Then I have to take the derivative of the inside, which would be negative sine y dy dx. Well, I already know that dy dx is cosine y minus 1 to the negative 1 power, so I'm going to plug this into here. So I have d squared y dx squared is equal to negative 1 cosine y minus 1 to the negative second power times negative sine y times cosine y minus 1 to the negative 1 power. Okay, well, these cosine y minus 1 to the negative 2, so this part and this part, both have negative exponents, so I have to bring them down to the bottom, which means I'm going to have 1 squared and 1 to the first power, which means they would be both to the third power. So this is d squared y over dx squared is equal to sine y, because negative times a negative is a positive, over cosine y minus 1 to the third power. This would be the second derivative.